Isomers are compounds that have the same formula but different structures. The isomers that we are going to talk about in this chapter mainly are constitutional isomers or structural isomers. They have the same formula but different connectivity, which means the carbons and hydrogens are connected in a different way. So let's first take a look at the molecule butane. Butane has 4 carbons, so I showed you 2 possible connectivity of 4 carbons. First one has 4 carbons in a linear chain, a continuous linear chain. Second one, we have 3 carbons in a continuous linear chain. The 4th carbon is connected to the 2nd carbon as a branch. So these 2 carbon chains are totally different, even though both of them have 4 carbons. Now let's put in all the hydrogens. Keep in mind that carbon makes 4 bonds. So that's how you determine how many hydrogens each carbon should have. So these are 2 isomers of butane. The first one, we call it N-butane. Second one, isobutane. N-butane, N here is abbreviation for normal. So all the linear chain alkane will be called the normal alkane. The branched chain will have a prefix in front of its name. For example, isobutane is an isomer of butane. So these are the common names for 2 butanes. Typically, the branches lower the boiling point and the melting point. So isobutane will have lower boiling point and melting point compared to normal butane. Some things that I want to point out here. We are talking about continuous carbon chain. So the 3 representations here all refers to the same molecule, normal butane, because the carbons are continuously connected to each other. It doesn't matter how the bonds are turned around. And for isobutane, these next 3 structures are the same for isobutane. We have a 3 carbon chain with a branch on carbon 2. So you need to differentiate these different representations of the same molecule from the isomers. Isomers have different connectivities. Next, let's take a look at pentane, the alkane with 5 carbons. So we can put the 5 carbons in a linear chain. One isomer of it, we only have a 4 carbon chain with a branch on carbon 2. And the next isomer, we have a 3 carbon chain with 2 branches, both on carbon 2. Let's put in all the hydrogens. Again, carbon makes 4 bonds. That's how you determine how many hydrogens we should have for each structure. The first linear chain is N-pentane, normal pentane. The second structure with one branch is called isopentane. The third structure with two branches is called neopentane. These are the common names of three isomers of pentane. I also want to introduce you a different representation of organic molecules, which are called line angle drawing. In line angle drawing, we use a line to represent a carbon-carbon bond, and the carbon-hydrogen bonds are omitted. So, for example, here are the structures of the three isomers of pentane. Keep in mind, a line means a carbon-carbon bond. So at the terminus of each line, there will be a carbon atom. We do not put carbon-hydrogen bonds in this line angle drawing. Again, if the bonds are turned around, but we still have a continuous chain, that's not going to change the molecule. So the three representations here are all normal butane because we have a 5-carbon continuous carbon chain. For isobutane, these three structures all represent the same molecule, isobutane. 4-carbon chain with a branch on carbon 2. You can count from either left to right or right to left, but we want to put the branches at a lower numbered carbon. So the branch is at carbon 2 for all three structures here. For neopentane, because we have one carbon in the middle that is bonded to 4 other carbon atoms, so there's only one way to show it. You won't see different representation for neopentane. Next, we will take a look at hexanes, 6 carbon atoms. And I'm going to use hexanes to show you how to systematically write all the isomers of a formula. So we will always start with the unbranched chain. The first isomer will be normal hexane with 6 carbons in a continuous chain. Next, we are going to shorten this chain by adding branches one by one. So we are going to remove 1 carbon from the 6-carbon chain and put it as a branch. You cannot put a branch on carbon 1 because if you put it on carbon 1, it will still be part of the continuous carbon chain. So we will start from carbon 2. This is the second isomer of hexane. Next, we are going to shift this branch along the carbon chain to make more new compounds. So we can shift it down to carbon 3, and this is a different compound from compound number 2. Now, if we continue to shift this branch to carbon 4, it actually becomes carbon 2. So we cannot shift this one branch anymore. Then what we are going to do is to remove one more carbon and put it as a branch. So now we have a 4-carbon chain, and we have one branch on carbon 2, one branch on carbon 3. We can also put these 2 branches on the same carbon atom, as shown in compound number 5. Okay, so these are all 5 isomers of hexane. Again, this structure represents compound number 2. Also, if you are considered 2 branches, you say, how about I put it on carbon 2 and carbon 4? Now, carbon 4 is a terminal carbon. When you put another carbon on it, it becomes internal. And this structure also represents compound number 2. 5-carbon chain with branch on carbon 2. So, when you draw isomers of a formula, you will always have to compare your new structure with the existing one to identify if they are the same or not. Now let's do one more. Heptanes, the alkanes with 7 carbon atoms. Again, we will start with the unbranched chain, the 7-carbon chain here. Next, we are going to remove 1 carbon and put it as a branch on carbon 2. So now we have a 6-carbon chain with a branch on carbon 2. We are going to shift this branch down the chain. Now the branch is on carbon 2. It's on carbon 3. Now 2 and 3 are 2 different compounds. If we continue to shift this 1-carbon branch to carbon number 4, which will become carbon number 3 if you count it from the right-hand side, which will make the identical compound as compound 3. So we cannot shift the carbon branch anymore. Now we are going to remove 1 more carbon from our parent chain. Now we have 2 carbons as branches. We can put them on carbon 2 and 3 or carbon 2 and 4. We cannot do 3 and 4 because in this case 3 and 4 will be the same as 2 and 3. We can also put these 2 branches on the same carbon, on the same carbon 2 or on the same carbon 3. Or even we can put 2 carbon branches as 1 branch, but now it's 1 branch with 2 carbon atoms. This is also different from any of the above. So previously we've seen that the 1-carbon branch cannot be put on the terminal carbon. We will have to start with carbon number 2. The 2-carbon branch cannot be put on carbon 2. It will have to start from carbon 3. Why? Because if we put it on carbon 2, it's going to change the longest continuous carbon chain. So imagine for compound number 8, if you are going to shift that 2-carbon branch to carbon 2, Which compound will that be? That will be exactly the same as compound number 3. So I hope you can draw that structure and see it yourself. We still have one more isomer for heptane. So we are done with 5 carbon chain. We are going to take one more carbon away from the chain. Now we have 4 carbon chain, and we have 3 carbon branches. Okay, 2 on carbon 2, 1 on carbon 3. And these are all the 9 isomers of heptanes. As you can see, as the number of carbon atoms increases in a formula, the number of isomers for that particular formula also increases dramatically. So as a result, it is very difficult for us to name each of these isomers by adding a prefix in front of, say, the name of heptane. So we will have to use some type of systematic ways to name this compound, which we will talk about in the next class. And the other thing I also want to point out is that in the periodical table, we have over 100 elements. Organic chemistry focuses on carbon atom and a few other atoms. The rest of the elements, over 100 elements, are all the subject of inorganic chemistry. Well, inorganic compounds, nowadays, we know it's still like 1/3 known inorganic compounds as compared to organic compounds. And the presence of isomers is the major contribution to the number of organic compounds being so big. Anyway, so I would like you to try to write out all the isomers for octanes, the alkanes with 8 carbon atoms. There are a total of 18 isomers. So I hope you can try to identify these 18 compounds.